just to make sure. I just want to make sure if it really started because I hit. Okay, awesome. We're on.
Yeah, you want to have a seat over here?
I'll step over to mine.
All right. Thank you. Yeah, welcome everyone. Yeah. So I'm Chad Yu. I'm the organizer of this meetup. Yeah. Mission is our assistant manager here. So yeah, I'm a data scientist at Axial Healthcare. Yeah. So our Great Nashville Healthcare Analytics meetup has been here in Nashville about 5 years. So yeah, we are people who are really working in healthcare analytics. We are open to anybody who is interested in this industry. So welcome everyone. If you are the first time, yeah, really welcome. But yeah, for those who coming back and giving us feedback, like fill out the survey, yeah, we really appreciate your help. So this is our survey page. Yeah, we will send out on the meetup after the meeting. So feel free to fill out. We really need your help. Yeah, to figure out what's the best time for our meeting, our location, any topics you are interested in, or either pizza. What kind of pizza you really like? Right? You know, yeah, we are analysts, right? We really like the numbers. Yeah. Also, we want to thank our sponsors. We have Axial Healthcare and Elevation Search Solutions. Also, this place, yeah, conference room is Vanderbilt Heart and Vascular Institute, their department conference room. So, yeah, let me really, yeah, we have Irene from Elevation Search Solutions. I want to give them a few minutes to talk about their, yeah, business. Yeah, if they have any job openings. So, Irene.
Hi, I'm Emily Martin. I am a recruiter with Elevation Search Solutions, and we are an executive recruiting and consulting firm. So basically what we do is we build out teams for tech and analytics teams for early stage or high growth or expanding companies. And we love to come to events like this to get to know all this tech talent in Nashville. And we're passionate about healthcare, we're passionate about technology, but we also fill sales roles, and we're kind of all over. So yeah, right now we're placing data scientists, we're placing senior data engineers, a few roles at the C-suite level, and we get new jobs on the board all the time. So I look forward to meeting any and all of you. I love to put faces to what is so important that is tech in Nashville, and yeah, thank you so much for letting us come and provide food and get to know you guys.
Now I'm going to introduce our speaker today. Yeah, Josh ROC, if I pronounce correctly. So Josh is a senior software developer at Extend Healthcare, and he is a really active contributor to the Healthcare.ai. So that's he's going to talking about that today. Before he moved to Nashville, he was director of solution architecture at King's Daughters Health System. So machine learning and artificial intelligence is really very hot topics in health care field. Yeah, this year. So it's kind of really hot this year. So yeah, so today Josh will present healthcare machine learning with Healthcare.ai. Please help me welcome Josh. Thank you.
All right, so hi everybody. I just want to thank you all for coming out tonight. I know many of you are probably very busy, and so hopefully the information I share will be valuable. But before we get started though, I do just want to ask a couple questions. So show of hands, how many of you in the room work in healthcare right now? Okay, that's great. And then how many of you have used machine learning or are familiar with machine learning tools? Wow, okay, that's a lot more than I expected. That's great. All right, so let's get started. So I'm going to present healthcare machine learning with a project called Healthcare.ai. So a little bit about me. Chad did a great job of introducing me, so I'm not going to go through all of this. I just want to say I'm from Ohio. I've been working in healthcare for about 9 years. Very recently moved to Nashville in July, and it's been great so far. I'm working with a company called Extend Healthcare as a senior software developer. And before working with Extend, I worked at a health system in Kentucky called King's Daughters Health System. During my time there, because I work on the solution architecture team, I was exposed to many different parts or many different areas within healthcare. So I was exposed to health information exchanges, remote patient monitoring, anesthesia billing, and of course analytics. So one of the projects at King's Daughters that we implemented, which was about a 2-year project, was a project called Health Catalyst, where we implemented a BI platform. Through that project, I met Health Catalyst data science team, and they gave me access to a very early version of the Healthcare.ai project that they hadn't released yet. And so we started using that tool at King's Daughters to do just some low-hanging fruit, like predicting patient no-shows, predicting readmissions. And then from that point on, I kind of started just contributing to the project as I had time. One more thing to know about me, and this is what I was just talking to May about, I absolutely love healthcare. I think it's a great field, and I hope it's one I get to stay in for quite a while. But before we get started talking about Healthcare.ai, I do just want to talk about the state of artificial intelligence and healthcare in general. And just so you know, when I say artificial intelligence, I'm kind of using it as a blanket term that includes deep learning, machine learning, predictive analytics, etc. So if you follow healthcare industry related news, you probably know that several big tech companies like IBM and Google and now Amazon have received a lot of press around their efforts to apply artificial intelligence to healthcare problems. Watson is probably the most visible, and whoops, sorry about that. I lost my mouse. Watson is probably the most visible, and in my opinion, probably the one with the most hype surrounding it. IBM's been aggressively marketing the project for years, claiming that soon it will be able to, and I think in some cases it already can, diagnose cancer. Google has several health-related initiatives. One particularly interesting one is a project called Calico, which seeks to establish a baseline for human health and prolong the human lifespan, and that one's using genomics. And then very recently, I think there was some stories released in the news about Amazon also looking to get into healthcare. So they have a project called 1492, where they may be dabbling in creating a EMR, which is electronic medical record, for those of you that aren't familiar. I also read that they are looking at telemedicine solutions, pharmaceutical delivery, and of course, introducing the Amazon Echo into operating rooms. But while these efforts are exciting, there is a problem, I think, with the way that they're portrayed in the press. So unfortunately, when a project like Watson makes a claim that it can identify cancer in a patient before a doctor, that somehow gets turned into a headline that says something like IBM Watson is soon going to replace doctors, or something like that. And I just want to show you just a few examples of this. So here is an article. I'm not going to share who these were published with, by the way, but here's an article where Watson made a claim that they recommend, or that they recommend the same treatment as doctors in 99% of cancer cases. Later, there was this article that said how 3D printing in IBM Watson could replace doctors. And if you read through that article, it kind of looks like it's based off of the information that's off of the other article. And then, of course, what happens is a few months later, there's an article that looks like this, where, you know, for some reason, IBM Watson didn't live up to the hype that it had originally, you know, to the claims it had originally made. And I don't think there's anything wrong with what Watson's doing. I think what Watson and Google and Amazon are doing, those are all amazing projects. The problem for me is just how we look at these tools, how these tools are portrayed in the news. It's unfortunate because what these headlines do is they create a lot of fear and uncertainty and unrealistic expectations. And then when the tools don't live up to the hype, people become cynical. Another problem I think caused by claims like this is that they tend to take the focus off of where the actual opportunities are. So these efforts by big tech companies really only focus on problems on the outskirts of healthcare. While impressive, they aren't really solving the practical problems that clinicians face from day to day. And I'm not alone in thinking this. So very recently, Leonard Diavolio, who's a Harvard professor and the CEO of a healthcare startup called Sift, said this recently at a healthcare analytics forum. He said, "We do ourselves a disservice when we refer to AI as something that can just take a ton of data, push a button, and cure cancer. We need to be more realistic around what these tools can and can't do." And then here's one more by another healthcare startup CEO. And I'm not going to read all of this, but I just want to highlight one thing he says here. He says the problem with the healthcare system isn't the doctors. He says a lot of people like to imagine a world where we can replace doctors with these tools, but people are flying from around the world to see our doctors. Instead, what we need to be focusing on is creating to provide a operational environment where the doctors can do their best work. And so that's one of the things that I think Healthcare.ai is really great at, and we'll get to that when we introduce the project here in a minute. So what are health systems like the one that I worked for, King's Daughters, facing on a day-to-day basis? So I want to talk about something called a LACE index. So throughout healthcare, there are many heuristics and established best practices that help clinicians make decisions. And the LACE index is a prominent example of that. So how many of you guys know what a LACE index is? Anybody? Okay, so 1, 2 people. All right, awesome. So for those of you that don't know, so let me back up. The LACE index does 2 things. It can predict, well, it's used to create a score that is supposed to be able to predict the risk of a patient readmitting or of dying within 30 days of discharge. So how many of you guys know what a readmission is? Okay. So for those that don't know, a readmission is an episode when a patient who's been discharged from the hospital is admitted again within a certain number of days. Health systems commonly use readmission rates as a common outcome measure and as a quality benchmark. So the LACE calculation is pretty simple. It's based on length of stay, the acuity of the admission, the patient comorbidities, and ED visits within the last 6 months. In each of these categories, points are assigned, and then the points are added up to form the index. While this is a very simple tool, it's also a really good example of how healthcare has worked for the last 20 or 30 years. First, someone does a national study, and then the study leads to guidelines, and then a simple calculation is created to help prioritize patients that are the most at risk of something. So what's wrong with that? Well, LACE was developed by patients that were seen in Ontario from 2004 to 2008. So now let me ask you, for those of you that work in healthcare, does your patient populations match the demographics of those of patients in Ontario in 2004 to 2008? No. So what happens, again, in health systems like the one that I worked at, we have analytical tools that will show LACE scores to our clinicians, but they're not terribly effective. And then the clinicians don't trust the scores, and then the resources get assigned misallocated, I guess I would say. So what kind of tools do health systems need? Well, it turns out there's a branch of analytics called predictive analytics that's getting a lot of attention in healthcare right now. It uses many techniques from data mining, statistics, modeling, machine learning, and artificial intelligence to analyze current data and make predictions about unknown future events. So a few months back, Becker's Hospital Review, which is a healthcare industry publication, published an article titled, "What are the most valuable outcomes to forecast with predictive analytics?" The survey was conducted earlier this year among 223 healthcare executives to reveal insights about the future of predictive analytic trends in the industry. And so here's a few things the survey found. So 57% of healthcare executives forecasted that predictive analytics would save their organization 15% or more over the next 5 years. 93% said that predictive analytics is important to the future of their business. So that's great. That means there's obviously a need for these tools. But where are the tools needed the most? What outcomes are the most important, most valuable to predict? So here's a list of the top 8 among healthcare providers. Patient satisfaction was selected the most at 53%, followed by readmissions at 48%. Now, one thing I want to highlight here is just where diagnosis is. You remember, those articles that I showed you from before. Well, just to kind of, highlight the need that health systems have versus, what you see in the media. Diagnosing was down at number 8. So healthcare executives are saying the most important things to them are patient satisfaction and hospital readmissions, not necessarily diagnosing patients. Not that that's not important, by the way. So why are these the most important outcomes to predict? Well, it turns out that there's a pretty big shift going on in healthcare right now, and those of you that are working in healthcare are probably very familiar with what I'm about ready to say next. So payers are kind of putting pressure on health systems to switch from a fee-for-service reimbursement model to a value-based reimbursement model. So in a fee-for-service model, healthcare providers are paid based on the number of services that they deliver to a patient. So in other words, that means that they are reimbursed based on the quantity of the services that they give to a patient versus the quality of the services. And a value-based care model, though, flips that. So the emphasis is placed on the quality of the patient's care. So instead of providing services to a patient and then sending them home to fend for themselves, healthcare providers are now being incentivized to keep people healthy after they leave the hospital. In other words, to provide a good outcome, which includes receiving positive feedback on patient satisfaction surveys and avoiding readmissions. So this is why outcomes like patient satisfaction, hospital readmissions are so valuable to healthcare providers. It's because they directly affect how the providers are reimbursed for the services that they provide, which is a good thing because in the end it ends up being what's best for the patient, what's best for the provider, and what's best for the patient or the payer, because it lowers the cost of providing these services. So there's a problem, though. Healthcare providers aren't well equipped to tackle these problems. If you work at a health system like the one that I worked at, I mean, we tend to think of health systems as being these large organizations that have very large revenues, but they're actually, in a lot of ways, starving for resources. So why are executives like? What are the biggest challenges to implementing predictive analytics in healthcare? Well, executives said lack of budget was an issue, regulatory issues, incomplete data, lack of skilled employees, lack of sufficient technology. So let's think about this for a minute. So there's clearly a need for predictive analytics in healthcare. Healthcare executives say that they believe these tools are going to save their organization significant amounts of money. Big tech companies can't help because either they're focusing on the wrong area or they don't have access to the rich clinical data that's available in electronic medical record systems. Executives are saying that they can't implement these tools because of concerns such as lack of budget, lack of skilled employees, or lack of sufficient technology. These are the problems that I think that Healthcare.ai, which I'm going to introduce here in the next slide, is very well positioned to solve. So with that said, let's take a look at the project. So what is Healthcare.ai? Have any of you guys, by the way, heard of Healthcare.ai yet? Have you guys looked at the website? Okay, great. So Healthcare.ai is first and foremost a community. It has education and it has open source tools, and it's focused on increasing the national adoption of machine learning in healthcare. So while companies like IBM and Google and Amazon are doing machine learning on the outskirts of healthcare, Healthcare.ai's aim is to work from the center where it can bring practical and accurate predictive models to health systems interested in improving outcomes. It has a growing website, which a few of you indicated that you'd been to, and it has a community that's focused on healthcare machine learning. They have on the website you can read and subscribe to weekly blog posts. They also do weekly YouTube live event broadcasts, and then you can even engage with the Healthcare.ai data science team via Slack or email, or they usually do Q&As during the live events. Some of the recent topics that they've covered on the broadcast include Machine Learning 101, Exploratory Data Analysis in R, Natural Language Processing. I think they may also have some a broadcast out there on XGBoost. And then recently they interviewed a data scientist at a healthcare startup out in San Francisco. So in addition to the community and the education, there's also an open source project that has packages in R and Python, which we'll do a demonstration of here in a few minutes. These packages are designed to streamline healthcare machine learning by including functionality that's specific to healthcare and simplifying the workflow of creating and deploying models. And these packages are designed, they're focused on solving practical problems like the ones that we talked about. So readmissions, patient satisfactions, not the big hairy problems like diagnosing. So who's Healthcare.ai for? So while data scientists in healthcare will likely find this project valuable, the target audience for Healthcare.ai are analysts, BI developers, data architects, SQL developers, or software developers that would love to create machine learning models with healthcare data. So why target these folks? Well, if you remember before from the results of those that survey, the healthcare systems like the one that I work for are starving for resources, and a lot of them don't always have the budget to hire a data scientist. But health systems do typically have BI developers and analysts already on staff. So what we wanted to do with the Healthcare.ai project is to create tools that was easy for those folks to use within their organizations. So now let's talk about the packages. So like I mentioned before, Healthcare.ai is available in both R and Python, which are two of the most common languages used for data science. Both projects are released under the MIT free software licenses, or under the MIT free software license, which is one of the most permissive out there. Oh, yes.
Regular data scientists, more of like a coding and analyst and BI, right?
Yes.
Would it make sense to like write packages in something which is more accessible to them rather than learning Python or R? Because like if I go to a BI analyst in my team and say that okay, we have Healthcare.ai package, please use it. They come back to me and say I don't know Python. Then what should
Yeah, so you don't really, so let me give you an example. So I do come from a software development background, so I'm cheating a little bit, but the first version of this project that I used was actually in R, and I don't know R. And I actually created and deployed a model with knowing very little R. So when we get to the demo, hopefully that'll answer your question. But what we've tried to do is create an API that's very, very simple to use. And I'll walk you through that. But the reason, I guess to answer your other question, why not create something completely new? It's mostly because R and Python have a huge amount of tools. For example, in Healthcare.ai, under the hood, what we're doing is we're just wrapping scikit-learn, and we're just providing a much simpler to use API. And then we've included some other tools as well, but just to give you an example there. So back to, Healthcare.ai is available in the MIT license. I'm sorry. under the MIT license. So the reason we did that was just to, hopefully avoid any legal issues or concerns that organizations may have. And both packages, I want to mention again, are just designed to solve practical problems. So while many machine learning projects are using advanced algorithms like deep learning, Healthcare.ai is instead focuses on, I guess, smaller problems. And they're using more of like the workhorses of the algorithm world. So random forest, logistic regression, those types of algorithms, which we'll look at. But both packages are being aggressively developed. So the R package just recently added the ability to do unsupervised learning and multi-class classifications. And then the Python package, the R package recently implemented XGBoost as well. The Python package, I think, has XGBoost under development and is currently has a neural network under development as well. So more features are being added all the time. If you don't have any experience with either project, like I mentioned before, my first time using this, I used the R package. It was pretty easy. I think the Python package is easy to use too, but I come from a Python background. I used it in college quite a bit. And then the R package does tend to have a few more features than the Python package does. The Python package just released version 1.0 probably less than a month ago. So let's talk about features. So Healthcare.ai, I think their features can be broken up into 3 groups. So it can analyze data using statistical methods that are relevant to healthcare. So Healthcare.ai provides statistical tools that are useful for analyzing healthcare data. It pays attention to longitudinal questions. And what that means is that often in healthcare, you are not working with just single records. You're often working with data where you're looking at a patient's history. So these statistical tools pay attention to questions like that, as well as the machine learning packages. And they also offer easy ways to do risk-adjusted comparisons. So in other words, being able to compare one population against another, or being able to compare a population with itself maybe like a year later, which is often useful to do in healthcare. So another feature that Healthcare.ai has is it makes it very, very easy to create, save, and deploy machine learning models. So it really kind of just, there's kind of a standard workflow that goes along with machine learning, where you have a data set, you engineer features, you create training and test sets, then you fit that to a model, and then you use that model to make predictions, and then you can deploy your predictions and deploy your model. Healthcare.ai takes that step and just makes it very, very simple. It also offers a few ways to compare and evaluate machine learning models. So again, since we're focusing on people that may be new to machine learning, we provide a few tools out of the box that provides guidance on how to pick the best model if they're comparing those. So I just want to take a minute to take a closer look at the healthcare statistics features that I mentioned a moment ago. And I'm not going to go through all of these. I do just want to highlight a few of these, though. These are all available in the R package, by the way. These aren't available in the Python package yet. But a few of the tools that are available in the R package are functions like functions for finding high variation. So in healthcare, outcomes improvement often comes from reducing variation. And that's a very important topic, especially now that a lot of health systems are encountering bundled payments. So I guess I'll use an example from our health system. So our health system probably about a year ago was selected for the cardiac bundle from Medicare. And so one of the things that we did with our patient population was we created analytical tools to try to find what the variance was with how our providers were treating our patients for, let's say, heart failure, for example. And the idea with bundled payments is that instead of being paid for each service you provide, the provider will receive one payment for an entire episode of care. So what that might mean is labs, having a procedure done, and then maybe being transitioned to some kind of a post-acute setting, they'll receive one bundle payment for that. So in that kind of scenario, variance is the enemy. You don't want providers that are offering services to a patient that they may not need, and then having another provider that's doing it for a much lower cost. You want your providers to have a low amount of variance. So this tool is very, very helpful for those kind of problems. Another example is to find trends. So often when you're working with healthcare data, it's usually helpful to see whether there's a particular measure that if you want it to trend down, like patient satisfaction or length of stay, the find trends function can help you with that. And then again, I mentioned the risk-adjusted comparisons. I think this tool is really cool. It just gives you the ability to compare populations against other populations or against itself if you want to, just to see if you're making improvements. And here's an example. So this is the R package, and this is the find variance function. And so what we're doing here is just loading in a bunch of fake departments, a bunch of fake genders, and length of stays. And then we're calling the find variance function on that data set and giving it some category columns and saying that the measure that we want to look at is length of stay. The important column to look at here is that measure impact column, which is just tell you where your most of your opportunity is. So in this case, it would be Department A, and their measure impact for length of stay is 5.19%, 5.19. So that's an area that you would want to look at for improvements. Another feature of Healthcare.ai is that it offers a streamlined workflow. So the Healthcare.ai has a very simple API, and we wanted to make it that way again, just to so that it would be easy to use for those that are new to these tools. So there's only really 3 things that you have to know in order to work with the Python package. So there's something called a supervised model trainer, there's an advanced model trainer, and then there's a trained supervised model. And the way that this works is that if someone is completely new to the package, they would want to use the supervised model trainer. You would give it some data. You would specify what column in the data that you want to predict and what kind of problem that you want to solve. So for example, do you want to do a regression problem or a classification problem? You would then call a algorithm on the function, or I'm sorry, on the trainer, and it would output a trained supervised model. And then you can use the trained supervised model to make predictions. It's pretty simple. And there's just a graph of the architecture. So the supervised model trainer wraps the advanced supervised model trainer. The supervised model trainer has a lot of defaults in place. So things like hyperparameter tuning, how to train and test, how to split your data into training and test sets, how to do data imputation. Those are things that you don't have to worry about with the supervised model trainer. We've already chosen some defaults for you in those cases. If you do want to do those things, then you want to use the advanced supervised model trainer, which lets you kind of peek under the hood and set those parameters. And then the trained supervised model, it allows you to look at metrics, model metadata, make predictions, and then save and deploy. And so here's a very simple example of the, this is about as minimal of an example I think that you can do with this. But what we're doing here is I'm loading 2 data sets. We have a Healthcare.ai ships with a sample diabetes data set. So I'm loading it into a training data frame and into a prediction data frame. I set up a supervised model trainer and I pass in the training data frame. I tell it that I want to do a classification. I want to predict whether or not a patient will readmit within 30 days. And then I give it a grain column, which really is just a key. And then that gives me the trainer. I'm sorry, I can hardly see the slide. So in the next section, I have a variable called train model. And what I do is I take the trainer and I call Logistic Regression, which is a machine learning algorithm. And so it will automatically just train a model on the data that I gave it using that algorithm. And then I can save the model if I want to use it later. In the next section, I have a variable called predictions, and I just say train model dot make predictions on my prediction data frame, and it will for all of those patients that have the same patient encounter ID, it will put in a probability that that patient readmitted within 30 days. And then you can save that. So pretty simple.
I have a question.
Yes, yes.
So in the project you are explaining, right? So each project will, like each hospital will have their own data sets, right? So is this system applicable for any data set?
Yes.
Okay.
Yeah, so you can load in data from SQL Server. I'm not showing all of that.
I mean, like when we prepare a final data set, right? So which we want to use.
Yeah. You can use any data. So right here, I'm just loading sample data right now, but you can load in data from, I mean, any column any column data, I guess, any kind of tabular data. And so really, if you're familiar with these tools, you're familiar with Pandas.
I use SAS, so I don't.
Oh, okay. So what the tool expects is that you're going to give it a Pandas data frame. So Pandas is a pretty common tool to use in Python for slicing and dicing data. But as long as you can get the data into Pandas, you can get it into Healthcare.ai.
Okay. And do you have like sample data set? I mean, like a complete project worked out, or is it just? Like
so in the in both packages there are examples. So there's examples of how to do classifications, examples of how to do regressions, and then some examples of how to do well, I guess an advanced example. I'm actually, the example that I'm going to show tonight, I took it right out of one of the examples in the project. So what we'll be doing tonight is very, very similar to what's in the package. And then if you want, you can just see me afterwards, and I can share the Jupyter notebook with you if you want to use that. So which algorithms are available in Healthcare.ai? So we have algorithms for supervised learning and then for unsupervised learning. And then we have some regression algorithms and classification algorithms. I'm not going to go through all of these, but there are little icons there on the left and the right that shows which package each of the algorithms are available in. I mentioned XGBoost before. That one's really popular in Kaggle competitions. I haven't used it myself yet, but I hear it's pretty great. So that one is currently available in the R package, and it's under development in the Python package. The Python package is currently adding a neural network, which I mentioned before. Tonight, in the example that I'm going to show, we're going to be using 3 of these, which I don't see logistic regression on there, but we'll be using logistic regression, random forest, and KNearest Neighbors in the demo. And then over here on the unsupervised side, we have the k-means algorithm that we can use to do clustering. So okay, let's do a demo. So I'm going to the demo I'm going to do is it's going to be in Jupyter, which is kind of like a live coding environment, I guess. Let me open the file. Okay, this is going to be interesting because I can't see that on my screen. So, okay, so what we're going to do for this training example, so I mentioned Healthcare.ai ships with a diabetes data set. And you can really do 2 kinds of, it's useful for, oh, thank you. It's useful for making 2 kinds of predictions. So the data set, the example that we're going to look at is a classification example, meaning that we're going to try to predict a yes or a no, but you can also do use it for regression problems like predicting a blood pressure, trying to predict a blood pressure, for example. But in this data set, there is 1,000 records. The data set's already pretty much cleaned up for us, so we're not really going to get into feature engineering or anything like that tonight. What we're going to try to predict is whether or not a patient will readmit within 30 days. So step one, what I'm going to do is load the Healthcare.ai package, which here's the relevant line right here. The rest of this is mostly just for this example. You wouldn't really need these if you're going to use the package. So let's do that. Okay, so let's see. Okay, so now it's loaded. So I mentioned that Healthcare.ai has several different ways to load data, as long as you're giving it a pandas data frame. So one option is to just load a sample data set. Right now we have one diabetes data set. I am currently working on adding several more from the University of California Irvine Machine Learning Library. Another option is just to load a flat file like a CSV. And then a third option is to load data from a SQL database. And so each of these just show how you would do that if that's something you wanted to do. So I'm going to skip that step. So what I'm going to do, I'm just going to load the sample diabetes data set, and then I'm just going to print out the first 5 rows so we can get a sense of what it looks like. Okay, so here's our data set. So we have a patient encounter ID, a patient ID, a systolic blood pressure, an LDL, which is cholesterol, and then we have something called an A1C, which is really referred to as a hemoglobin A1C. I'm not a clinician, but I'm going to try to, I guess, describe this as best I can. So hemoglobin A1C is, I think, kind of like an average of your blood sugar over a period of time. Is that right? Yes, thank you. And then for some reason, we can't see it, but there's also a 30-day readmit flag. So this might, wonder where that went. Okay, well, let's go ahead because we'll get to that here in a minute. So one thing that we're going to do here is we're just going to drop the patient ID because it's not going to be really useful for us in this example. So here's what our data set looks like. Oh, there's our readmit flag. I guess it was just cut off. So now here's our data set without the patient ID. So now, typically with machine learning, one thing that you want to do is just kind of get a sense of the data you're working with. I just want to take a look here. So what this line is going to do is it's just going to group the columns, or I'm sorry, group the data set by the 30-day readmit flag. And then it's just going to give me a count of the yes or the no's, because I just want to know kind of what kind of data I'm working with here. So we can see here, I have 1,000 records. I have 836 patients that did not have a readmission, and I have 154 visits that did end up being a readmission. And then one more. What this one's going to do is it's just going to graph out the A1C, the systolic blood pressure, and the LDL, just so we can see. And it's going to group that by the 30-day readmit flag, so we can see what those numbers look like for patients that readmitted versus those that didn't. Okay, so here, this is our A1C. And so just looking at this at first glance, one thing I can tell here is that we had a lot of patients that didn't readmit that had A1Cs in the 5, 6, and 7 range, but we also had a huge majority of patients that had readmissions were in a very high range for their A1C. The systolic blood pressure, again, I'm not a clinician. This doesn't look terribly significant to me, but maybe someone that is a clinician that would be able to see something valuable here. Last one, cholesterol. So it looks like, again, looks to me, patients with high cholesterol are much more likely to have a readmission than those that don't. So step 2. So now that we have our data loaded and we've kind of got a sense of what it looks like, we're going to use the supervised model trainer, which is the simpler option that already has some defaults in place for us, to create a trainer. So I'm going to run that, and then I'm going to print out what the data frame looks like after I run the trainer. Okay, so I loaded my data into the trainer. I told it which column I wanted to create a prediction. I wanted to make a prediction on. I told it what kind of prediction I wanted to do, and then I told it what the key column was. I also told it that I wanted to impute data. So what that means is typically in machine learning, when you're working with data, you don't always have values in all of the fields that are significant. So for example, while you would think that all patients have a blood pressure, sometimes when you get data, there may not be a blood pressure in that particular field for some reason. Maybe it wasn't documented or whatever. Maybe you may not have an A1C. So what the supervised model trainer does is under the hood, it runs a data pipeline. And the data pipeline will try to impute those values, those empty fields. And it has a few different ways of doing that. So if you're working with categorical data, like maybe like a department, it will take the mode, which is the most common in the data set, and it will impute that value. If you're working with data like a blood pressure, it will try to impute the mean. What's cool about Healthcare.ai, and this is part of the reason that we have a grain column up here, is it will try to do that imputation based on the grain that you selected. Meaning if I have a bunch of patients, if I have data from or multiple rows for the same patient, it will try to impute the data based on that patient's information rather than the entire data set. So it will do the imputation for, like, let's say that the average blood pressure, I don't even know like what a good range is, would be like 120 or something like that. And then we have one patient that has a very, very high blood pressure. It wouldn't make sense to impute 120 for that patient. We would obviously want to impute something that's within their normal range. And so behind the scenes, this did that. Another thing it did was that it kind of made my, it cleaned up my data a little bit too. If you remember, for the gender flags, I had an M and an F. So what it did with that was it transformed it into a flag that indicates whether or not you're a male. And then for the 30-day readmit flag, it took the yes and no and it converted it to a 0 and a 1. And that's necessary just for the algorithms that we're going to use. They can't make sense of yes or no's or M or F's or whatever. You typically have to convert those to some kind of a numeric value. And so that's why the trainer did that. So now our data is ready. The next thing we're going to do here is just train some models. So the first model that we're going to train is a logistic regression model. So this is a technique that's no. Let me back up a second. So it's called logistic regression, but it's mostly used for classification problems. So don't be confused by that. It's named for a function that it uses at the core of the method called the logistic function. Not really necessary to know, if you're just getting started with these tools. What we're going to do is I'm just going to train the model, and I'm just going to save it to a variable called trained LR. So let's run that. Okay, so that gave us some output. So it told us what our training time was. It told us if it found any hyperparameters. Hyperparameters, by the way, if you aren't familiar with that term, are just parameters. This screen keeps scrolling. It's like messing with me. It's okay. It's fine. So hyperparameters are parameters that you can pass into a machine learning algorithm to tune or optimize its performance. And so sometimes whenever some of these algorithms, when you run them, it will Dataset and it will recommend hyperparameters to you. In this case, we didn't have any. It also gave us an accuracy. So we can see that our accuracy was 88%. And then it gave us something called a ROC AUC and a PR AUC. I'm not going to go over those yet. We'll talk about those here in just a minute. Another thing that you can do with this particular, so now that we have a trained supervised model, which is in our trained LR, we can use it to create plots. And the plots are used to help us evaluate the performance of our model. So I'm gonna run two. I'm gonna do a ROC plot and a PR plot. And so these are useful for kind of figuring out how accurate your predictions are. Again, I'm not going to talk about this right now. We'll talk about this here in a minute when we get down here to compare these. So next model that we're going to do is one called KNearest Neighbors. So like logistic regression, KNearest Neighbors is a can be used for classifications. In order to classify a point, it combines the classification of the k-nearest points. So let's run that. And so this gave us some information as well. It told us some weights, told us the training time. This one did suggest some hyperparameters for us. And then it also gave us an accuracy and the ROC and the PR score as well. I'm not going to plot that one. And then the last one is an algorithm called random forest. So random forest uses, it's an ensemble learning method for classification or regression, and it operates by constructing a multitude of decision trees at training time, and then putting the class, in our case, that's the mode, the most common of the classes of the individual trees that it creates. So let's train that one. So this one's kind of cool, by the way. It takes a little longer to train, but what it can do is it will actually show us which of the features that we passed in were the most important. So again, we got some information about our model. The accuracy, you can see the accuracy on this one was better than the other two. So just looking here, so one thing that's cool about the way that random forest is set up in the Healthcare.ai package is it will actually tell you which of your features are the most important. So you remember before, I was looking at the systolic blood pressure, and I couldn't really, by looking at it, make a lot of sense out of that. Random forest, obviously, though, thought it was pretty useful for some reason. It also indicated that the A1C was important and that the LDL was important as well. The gender turned out to be not useful, so going forward we could just drop that whenever we actually go to deploy our model. Not really necessary. So if you're doing exploratory work, like for example, like let's say that you're working with some data and you're not really sure columns in the data set to use to make predictions, you can feed them into random forest like this, and random forest will actually tell you which columns it thinks is the most predictive. So that's a useful feature. And again, we could just plot that. And so we can see here that it had a pretty good ROC curve. The PR curve wasn't very great. The next thing you want to do, so now that we've trained some models, is we want to compare those models and just get a sense of which one is the best one. So I mentioned before, I kind of glossed over the ROC and the precision recall plot. So those are the two methods that Healthcare.ai gives you to evaluate your models. And they're particularly useful for evaluating classification problems. So what I'm going to do here is I'm going to load my 3 models that I trained into a list called models to compare. And then I'm going to plot a ROC curve and a PR curve for all of the models. So let's do the ROC curve first. So the ROC curve is useful because it compares your model's true positive rate with its false positive rate. So your true positive rate is the amount of yeses that you predicted that actually ended up being yes, and the false positive rate is the amount of yeses that you predicted that were actually nos. So the ideal curve to have when you're training a model is to have a curve that's high and to the left. You want all of your false positives, you want a majority of true positives, and you want no false positives. This point that's marked here with a star is the ideal cutoff point. So under the hood, that's the point at which Healthcare.ai used to determine whether to predict a yes or a no for that particular column. And you can tweak that if you want to. So this is the point where the true positive rate was the highest, and the false positive rate was also at the lowest value. And so looking at this may be a little confusing, but the idea here is that you want a model that has something called a high area under the curve, meaning that it maximizes the area over here to the right. And a model with a high area under the curve, meaning that like the ideal model would cover this entire chart, for example, would be a perfect model. So the closer you get to this upper left-hand corner, the more accurate your model is. So what we do here, down here at the bottom, is we actually tell you what your the area under the curve is. And it's like, if you're going to use, since you're just starting out, if you're going to use one score to evaluate a model, the area under the curve is pretty useful. So here we see that the random forest, which is the red line, has the highest area under the curve. So right now it's looking like that's probably the best one in this particular case. However, whenever you are training models, one thing to keep in mind is whether or not you're working with imbalanced classes. Yes?
Not quite following with the graph on there. Is that the predictions as it goes through time and it gets improved? I can't quite read that.
Oh, I'm sorry. So this is your so on the y-axis is your true positive rate, and on the x-axis is your false positive rate. What you're looking at here, the line is following every possible decision point that the model could have used to predict a yes or a no. So sometimes you don't want to predict, let's say that you are trying to diagnose a patient. So a high rate of false positives would be very dangerous in that scenario. So you would want your cutoff point maybe to be down here where you have much less false positives. You want a high amount of true positives. But let's say that we're working with patient no-show data. So not necessarily as important if we have a high number of false positives. So we may want to move our decision point up here on the line some more and have our model make the decision at another point in the graph. Does that help at all?
So as the graph's moving, it's looking at different coefficients and weights?
No, it's not looking at different coefficients and weights. It's really just, I can't remember the formula right off, but it's really just like the true positive over the, trying to remember, Chad, do you know? It's the true positive over the false positive plus the false negative, I think. I can share the graphs with you, how it calculates those scores. But essentially that's what it's doing. Yes?
Basically, what the model does is it gives you one number. Okay, it's like a prediction between you and him. And it does that for all the time, right? So what it really does at that point is that, if you say that, okay, any number below certain threshold is class 1 and above is another class, right? You move that threshold around, up and down, then your true positive and your false positive is different, right? Depending on the threshold. So that is what your following is. Every point on that curve corresponds to one such threshold, and the corresponding true positive.
Yeah.
So the optimal point is where, as he said, you want that curve to have as much area as possible. What it basically means is that your true positive rate is true positive basically is that how many samples you can actually accurately identify as their real class, right? So you want that to be high at the same time. You don't want to do the opposite, that is misclassify, right? So that's why if the curve is pretty much high, at some point this optimal is where that's the best threshold. The model automatically picks that threshold that you apply to that. But my question following that is there a way for you, usually when we do modeling, right? Mm-hmm. There is no way to pick that threshold because the model does that for you when you do the prediction. There are predicting methods following, right? Mm-hmm. But is there a way in which we can actually get to that data behind that graph and pick up our own threshold?
Yeah. So under the hood, I mentioned before that this is using scikit-learn. If I remember correctly, there is a function. I think it's called decision function, possibly. And instead of outputting the predictions or the probabilities, it will actually put off and let you select the cutoff point in that with that tool. You have to double check me on that, but I think that's.
Even like the R package, like the ROC package or something, you can actually profile. You can basically give like a grid. It tells you what are the values, the specificity and sensitivity by cutoff. It takes some time to do that, but you can get that and have a good idea. There are packages to do that. Yeah.
One other thing, real quick, I didn't even mention this. One thing that may be useful is to, I guess I'll do it here. You can get those metrics if you want them. I call them metrics. So here's kind of what all that information looks like under the hood. If you see, here's your thresholds right here for your ROC plot. And that's what those look like. So if you wanted to see those and wanted to do something with those, you could get to them. Okay, so we looked at the ROC curve. Now, so another tool that we have is something called a precision recall curve. The precision recall curve is particularly useful whenever you're dealing with imbalanced classes, like we're dealing with here. So we have a lot of no's, meaning we have a lot of patients that didn't readmit, and we have a handful of patients comparatively that did readmit. So what this is going to do is it's going to show us the trade-off between precision and recall for different thresholds. So remember that I was talking about high area under the curve, or I was talking about area under the curve. So in this chart, a high area under the curve is going to represent both high recall and high precision, where high precision relates to a low false positive rate and high recall relates to a low false negative rate. Meaning that this time we're taking those into account rather than just comparing yeses. So high scores for both show that the classifier is returning accurate results, meaning it has high precision, as well as returning a majority of all positive results, or all of the positive results. So let's look at that curve. So this one, our models, I mean, really, I guess the point to make here is that you would look at the ROC curve and you would think, oh, I did pretty good. Let's deploy this random forest model. But since we're working with imbalanced classes, if we go down here and look at the precision recall curve, you can see that we're kind of just following the line here, meaning that we really didn't do that great. The ideal curve for a precision recall curve is to be over here in the high right hand, in the top right hand corner, meaning that you have recall on the bottom, precision on the y-axis. So you want to have a high precision and a high recall. I'm running a little low on time, so I'm going to stop there. But just kind of keep that in mind. As a rule of thumb, when you are working with imbalanced classes like we're working with here, you typically want to use the PR plot. If you're going to use one thing to kind of evaluate your model, you typically want to use the PR plot rather than the ROC plot. So we have so we trained a model. We're going to pick the random forest one because although it wasn't the greatest ever, it did perform better than the other two. So to save your model, we would just call train random forest.save, and what that would do is just save the model as a binary file, and then you could load that later to use it to make predictions whenever you get new data. So I'm going to skip that step because we're just going to go ahead and use it. So now we're going to use our model to make predictions. So what I'm going to do here is I'm just going to reload the same data set that I had before so that we can compare it at the end to see how we did. I'm going to drop the 30-day readmit flag. So we're going to pretend this is all new patients that have no readmissions. Like we don't know whether or not they're going to have a readmission. So let's do that, and let's print out what we have. So you can see here I have a new data set. The 30-day readmit flag is gone. And what I'm going to do is I'm going to take my train random forest, and I'm just going to call make predictions, and I'm going to pass in that same data frame, or that data frame, and then I'm just going to print out what I get. So here's the first 5 predictions that it made. So by default, with classification problems, what Healthcare.ai gives you is a probability score. So if you remember, the first 5 records in our data set were all no's. So what you're looking at here is the first record had a probability of 2% of being a readmission. So that's good. Anything below 50 would be a no. Anything above 50 would be a yes. 3% for the second patient, 2%, and then 0% for the next 2. So that actually looks pretty good. So there's a few other ways that you can kind of get your data out. So, you know, I called make predictions, and it just gave me my prediction back. If you want to save this data off to a database and maybe, you know, display it in a visual tool like Tableau, there's other ways to get to it. We'll show you what the top factors were if that information would be useful for some reason. So, and this is for each record, by the way. This isn't for the entire data set. So for this record, the most important factors were A1C, LDL, and systolic in that order. For other records, it may be systolic may have been the most important factor. Another way to get your data out is, I can't read all this one. I don't remember which one this is. Oh, so this one gives you your top factors, and it gives you the prediction if you want that. And then this one will give you, I think, the entire original data set with the factors, there we go, and the prediction. And so you could take that and just you could save it off to a database if you wanted to. The last thing I'm going to do here is just I'm going to take this data, this prediction data, and I'm going to compare it to the original data that we loaded in. And just compare the yeses with the nos, just so you can kind of get a sense of how accurate we were. So let's run that. So what you can see here is I just created a category for nos and yeses. So in our original data set, we had 828 nos, and we actually predicted 828 nos. So we had we had 8 nos in our original data set that we predicted to be yeses. We had let's see, 18 yeses in our original data set that we predicted to be nos, and then we had 136 yeses that we predicted to be yeses. So that's actually not bad. So out of 1,000 records, we had 26 incorrect predictions. So not terrible. And that was also, you know, I just split those right at 50%. So some of those may have been a low probability of being a yes or a no.
They say you've got a 74% accuracy.
74% accuracy. No, that would be 7.4% accuracy. No, sorry, 92.6% accuracy.
So, you know, using data model, do you check why they make a wrong that just because you?
So what I did here, so I'm not taking the probability into account. Like I said, I just split it right at 50%. Some of these may be a low probability that I actually predicted. Like if I were to actually look at what the probability scores are for these particular records, the probability of it being a yes may have been like 51%. And I may have wanted to maybe set the threshold a little bit higher or something for that particular scenario. But this was just, you know, kind of to give an example. Yes?
This is the same data training model.
It is, yeah, and well, yeah. So the model isn't going to learn the data perfectly, right? And I didn't do any kind of feature engineering on the data either. It was already kind of cleaned up. But yeah, it's not going to perfectly learn the model, and that's just one thing to keep in mind here. Anytime you train a machine learning algorithm, it's not going to be able to make the exact same predictions that you trained it on. But it should be able to get close, and that's the ideal case. So the last thing is you can save your predictions. So we can save those to a comma separated value, or we can save those to a database. So that's it for the demonstration. I do just want to mention very quickly how this is being used in the real world. So currently, Healthcare.ai is being used to save more than $1 million annually by predicting financial codes at a major health system. It's also reducing central line infection rates by greater than 50% at a large academic medical center. It's lowering patient financial burden across 150,000 patients per month at a large Midwest health system. And then it's also helping clinicians and operations to prioritize resources with predictions for models across readmissions, infection, and finance. And so that's it. Anybody have any questions? Yes.
London Forest, how much can we improve comparing with regular decision tree?
I'm not sure I quite understand. I mean,
so I mean, if we compare London Forest with regular decision tree, that's a general way.
Yeah, I mean, I guess I would, have to have a way to.
10%?
Yeah, I mean, I don't know. I guess it really depends on what the data is.
So it's not like class, or it's not general result.
No, I mean, like I said, so it would really depend on the data that you're working with. Like, you wouldn't be able to just generally say, like, random forest is going to be 5% better than, a regular decision tree or a logistic regression or whatever. Some algorithms are better with some data versus other, and then some algorithms are better with a certain number of columns. Some are better with a certain number of rows. It's really just going to depend on what it's highly dependent on what data that you're presenting to the algorithm. Anyone else?
So this Healthcare.ai is just an open source tool.
Yeah, just an open source tool. You can go. I don't work for Health Catalyst. I contribute to the project. I mean, it's out there on GitHub. You can contribute, add features. That's what I do. I mean, I do know the guys on the team, but I don't think I just do it in my own free time, like anybody else. Yes.
So did you do any benchmark against, say, scikit-learn or XGBoost packaging?
So this tool actually is using scikit-learn under the hood. So yeah.
That's what I thought. It's basically a big wrapper and automated a lot of stuff.
Yeah, exactly. So that's kind of what we did. We tried to set pretty good defaults for several of the algorithms, and then we also kind of made some decisions around how we do training and testing splits on your data. Again, just to kind of make it easier for folks that may not come from a software development background or a data science background, to make it easier for this to use this tool.
You look at all in the data ingestion side, we're headed for a lot of these types of problems, getting the data in these formats. You guys work all the time.
No, so right now, we're kind of just leaving that problem up to you to solve. Really the only tools that the package has is being able to load the data from some kind of a data source like SQL Server or Oracle or MySQL, for example. But we really don't have any tools in place yet to handle ingesting large amounts of data. But there probably are other Python tools that can help you with that.
There are multiple ways of looking at data. So if you're looking at like one computer, like an example, somebody you just have to use it really the constraint is hard, right? So you can have a process on a server.
I guess my question was more that given this is a wrapper for healthcare, I would assume that some of the input data you're going to see commonalities across healthcare, which is the providers or whatever the data source comes out of. There were certain essentially like other wrappers tailored to healthcare.
Oh, trying to
So
think.
you're
Like,
talking about the common data models that we have right now, right? Basically, but it's kind of difficult to develop that. Imagine, right? Like, you see that people use all over the place. Like, one health system, one department uses a different product, not just like they might be using SQL Server, the other uses some other database, somebody uses like a Teradata.
That's exactly.
So as a product standpoint, it's not. So what you're trying to say, I don't think they're trying to aim to that.
yeah.
Other products which do it, like the master data management.
Yeah, there's, I was going to mention too, so I worked with health information exchanges quite a bit at King's Daughters, and one thing that we had looked into, so there's a new standard that hasn't been widely adopted yet, but I know it's in some EMRs like Epic, that is looking to be a replacement for HL7, and it's called FHIR. And it's kind of like taking, trying to modernize HL7 and make it more similar to the way that we pass data around in web-based projects. So it's more of like a RESTful kind of format. There is a project that's related to FHIR that was called Smart on FHIR, and what it tried to do was create some data models that you could use out of the box, like a common data model for a patient, a common data model for a encounter or something like that, for example. But I don't know that it got very far.
I was one of the early sandbox users.
Uh-huh.
FHIR, not on FHIR, because I used to work for a large hospital management company, and they were like similar times. So
yeah.
So the problem was that they got too ambitious. Even before trying to get the product to have a good sell or to have a buy-in for people, they wanted to grab it and sell it. Make
right.
money out of
Yeah.
it. And that basically put out a lot of people. They did not even want to get the buy. So I think it's still there, but they are just like ad hoc products here and there.
Yeah.
Using that, it could have been better.
Yeah.
It was actually, I was very excited about FHIR at some point. So yeah, the FHIR was doing that. They were basically creating a master data model. So the idea was that you can ingest from different sources and then basically QA data.
Oh, I guess I should end the broadcast now.
What do you say? Data store sort of thing. But that was hosted